Okay, we're live.
Yes, this is the first time, huh?
Yes, Deep Tech Podcast. Is that what we are calling
Yeah, this is gonna be the one.
it? Okay.
So to tell you what we are doing here, every day we are working with a lot of deep tech companies, and we learn a lot from the deep dives that we do using our AI tools and such. We thought that it's cool also for us to share between each other this information and these learnings, and also maybe it's interesting for some people out there to get to know these. So we are learning these, how to do this work, and it's gonna be very unpolished. We are not gonna spend a lot of time editing this. See how we go.
Yeah, yes. Talk about what we learn every
Yeah,
week. I think there's this ecosystem, there's these companies that have been there for ages, for 50, 60, sometimes 80 years. These very strong companies that no one knows about, that they make, the most complex technologies in the world, the most advanced scientific products. And I think they are a bit underrated. We interact with them a lot in our day to day, and I feel like people need to know more about them. There's a lot of startups in this area as well.
yeah,
I think in the last couple of years it has been very strong trend that more and more of the new generation of startups are more based on science, biology, semiconductors, battery, energy. It's less and less, about apps and software. I'm
yeah,
a computer scientist. We are a software company, but I still feel like, we are not the ones really doing the high tech. Like these are the companies doing the high
yeah.
tech.
When we were coming, when I came out of science
Yeah.
and focusing helping scientific companies actually work better and like expand their network and such, we were never the ones that like among the cool ones,
Yeah, yeah,
right?
yeah, yeah.
All of these app companies, they were the cool
Yeah, yeah, yeah.
companies, but now it's shifting. Like last in 2022, only I think 60 to 70% of the investment from VCs went to deep tech companies.
Yeah.
Yeah,
I think we are in a unique, weird position where, we can talk very deep about the science, and we can talk about the markets and the business, and our bread and butter is AI. So we have this weird intersection. We don't know as much as other people for a specific thing, but I think we can have a fresh perspective. um yeah,
so
we wanted to talk about today mostly about the semiconductor market. We were focusing on that lately in the last few weeks. Yes.
but before everything else, what do you mean by deep tech? Let's go through
Okay.
that.
Yes.
What is deep tech?
What do you mean by deep tech? For me, it's companies that have a strong scientific foundation, that need a lot of R&D, that have a competitive advantage because they take advantage of uh, the latest advancements in science. They have strong connections with academia. They have products that are quite hard to produce and require very advanced instrumentation to produce.
Yeah.
To me, these are the deep tech companies.
Yeah, I quote here from my research that I did on MIT, articles from MIT and also McKinsey. There are multiple ways that people define them. It's a essentially is no vertical is very well defined. If you can essentially define it as a way that is both complete and also covers all of the um, examples, but here that's how they find it. A market sector that is located at the technological frontier today.
Mhm,
It has two components: the existence of high level of information asymmetry, so essentially knowledge,
mhm,
the presence of high level of capital intensity.
mhm,
So,
mhm,
so deep tech today might not be deep tech tomorrow
mhm.
because it needs to be at the edge of technological frontier. So you need to have a lot of knowledge to push that frontier, and at the same time, you need to have a lot of capital, invest a lot of capital, hire a lot of technical people to be able to push that forward.
I think like in practice, you know, it's deep tech is different to everyone, but I think in practice it's mostly used to indicate what it's not. You know, tech has been a big thing for a long time, and deep tech is just kind of to distinguish from that, to separate on that. You know, this is not a normal tech company; it's a deep tech company. You know, they do real
So
science.
essentially, all tech used to be deep tech,
Sure, sure.
and tech became too
But now, like,
vain and like too
yes.
kind of general.
Well, it
Now,
used to be talked like called high tech, but
yeah,
now everything is high tech. So we
yeah.
changed the name. Huh?
Like you can make Uber is high tech.
Yeah, yeah,
If you
yeah,
make a pizza delivery app is high tech,
yeah, yeah, yeah,
which is anything by high tech,
yeah, yeah, yeah.
but high tech. So one of these fields, which is very much talked about, and we are really coming across it very often, is semiconductor
Yeah.
and computer hardware. Compute hardware. There is quantum computing there as well, and electronic devices. But let's focus on semiconductors.
Yeah.
Can you tell me like what you feel why it has become so serious? You have been reading also the
Yeah, yeah,
Chip
yeah,
Wars
yeah, yeah, yeah.
book. Why it has become so hot right now?
Like it was like in the past, it was the hottest, vertical, the hottest industry, from the 70s, 80s, 90s. Like, it's called Silicon Valley. That's where everything came from, all the money came from, all the, new technologies nowadays, even like stuff that seems totally different, like biomedical stuff. It's all fed by new advancements in semiconductors. It's just been the last like 15 years where it has taken a bit of a backstage, with this new generation of, Facebook, Google, Microsoft. Well, Microsoft is a while ago, Apple is a while ago, but they started with semiconductors, the beginning of the PCs.
Microsoft,
Yes, yes.
microchip software.
So it has taken a bit of a backstage lately, and the whole world has been focused on software, but I think this is temporary. And now with COVID and the whole geopolitical situation, it's becoming more and more obvious how important and fragile the whole semiconductor ecosystem is, and there's a lot more attention in making that more robust and really realizing that it's the foundation of everything.
Yeah, but okay, very good. There are two things I see that, or three things that is been fed this, and one was essentially, yeah, from my point of view, when I was doing research last few weeks on it, apparently the start of it was what essentially geopolitics, and then very complex supply chain, which makes it very fragile.
Yeah,
And the other one is like the rise of AI and new advanced chips that we need.
yeah, yeah. I think there's like two new trends again. Like one is uh becoming a bit independent of companies like TSMC or Samsung, who are right now the only companies in the world that can make the most advanced, chips that everyone uses. Like all the Apple produces everything at TSMC, Nvidia produces everything at TSMC. The whole AI situation is all reliant on these few companies. So I think the world is trying to diversify from that because it's a bit fragile, trying to build more fabs in the West, in US, in Europe, also Japan. China is fighting really hard to be able to make their own semiconductors. So this is one trend, increasing the capacity and diversifying how semiconductors can be made. And the other trend is the same story as always, Moore's law, going again like smaller node. Now we are moving towards 3 nanometer nodes, and crazy science and engineering is required for this. And there's also market trends for this, market bottlenecks, where, for example, ASML is the only one that can do this right now. And there are big movements in this area, so there's a lot of investment in R&D, and there's a lot of investment in creating new fabs, increasing capacity, and diversifying the production. um, yes. Uh, we were particularly looking at the opportunities for, because uh, just to give a
Sure.
bit of context, like we have always worked a lot with kind of precision instrumentation companies. Our roots are in academia, in science. We were the bridge between science and business. We have helped a lot of companies sell their scientific instrumentation to academia. And now we are also helping industry. So we are looking at what the opportunities are specifically for these companies in semiconductors. We saw that we need to focus on R&D and quality control and failure analysis. I was looking at some numbers in there. But what do you think? Like you have been looking at this a lot, talking to these companies. What is the feeling?
Yeah, but sorry guys, first I don't know, I have some allergies that I cannot control my coughing. I'm
It's
not sick.
fine. It's authentic. It's
Yeah,
fine.
I yeah, it's every time in my meetings and such with customers.
Yes.
This comes up and they feel that I'm having persistent, what do you call it? The long COVID,
Yes. 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 Yes.
but it's not. It's allergies. It's worse than long COVID.
Mhm.
Um, the thing is that, like, the last 2 3 years, more than $250 billion was invested in the U.S. alone
Mhm.
for building new facilities.
Mhm.
And before this, everyone was moving towards fabless. A lot of companies were fabless, and they were essentially all the production or dirty work, let's say,
Mhm.
was moved to East Asia.
Well, it's like at first it was because of just cheaper labor, but more and more I think it was just because it's so hard to make the new semiconductors. So you really have to centralize it. Like the only way you can manage is if everyone in the world like unify their resources and everyone makes their chips in a single place. And that way, with all these resources, you can make such advanced chips. But yeah, otherwise it's really hard for each company to have their own manufacturing. Yeah?
Yeah, I'm trying to ask, like, because we are in the Netherlands now, so ASML is a Dutch company, but I'm always questioning and asking why TSMC can make highest um, precision, or what they call smallest nanometer nodes
Hmm.
than everyone else, if everyone else has the highest and best machines.
Yeah, I think. Well, I think it's all ASML. I think they all use the same machines. I think the difference with TSMC is they have the clients. They have the biggest clients in the world, and they have the resources to fund the newest fabs because everyone relies on them. I don't think they have a particular advantage because TSMC doesn't invest as much as, for example, Intel invests like 20% of the revenue, yearly revenue in R&D. TSMC only invests about 8% of the revenue in R&D. So they don't do that much of their own. They rely on other companies to advance their technology. And both Intel and TSMC they have similar revenue every year. I think it was both they make about 60 billion a year. So I think the advantage of TSMC is mostly about business. The strategic. Intel only has themselves as a client, and they are trying to build a foundry. I think they
No,
have been
they
trying.
are. The latest CEO made it
Yeah.
like they made the foundry separate from the design.
Yes, I think so. They are trying, but I think it has slightly flopped. I think they are pushing it a bit further and trying again, but uh, yeah, still it's hard to capture the market. So yeah, I think that's why TSMC has the newest stuff because they can afford it.
Yeah. So let's move to the semiconductor supply chain
Yeah, yeah, yeah.
because
I don't want to go a bit deeper, like deep tech. We have been giving an
yeah,
overview, but I would like to nerd out a bit about the science and go a bit more in detail
yeah,
into this
I would
kind of
can we can
manufacturing
go to
process.
the science and manufacturing process, but like the thing is that like uh, semiconductor industry has a very strange and intercombined, like any other industry, I assume, uh, like supply chain. I'm now looking through the supply chain that I mapped. Uh, so it starts from raw materials that essentially they need to. There are a few companies that make those essentially the silicon.
Is this a bottleneck? Like, uh, I mean, silicon is fairly abundant. I don't know if it's very hard to get the silicon to a state that is, accurate enough for the wafers. Is that a bottleneck in the market, or are there many suppliers for that? Do you know?
I know there are actually the three suppliers of it,
Hmm.
and also they do pre-coating,
How
and
are these made actually? Do you know? Because I don't
they
know the
melt them and
details.
they essentially drop them as a drop, or like what you call big,
Hmm.
like silicon drops
Because they need to be
for
a single
wafers.
crystal, don't they? Like a single crystalline structure.
Yeah, I don't think so.
No? Okay.
I don't know.
Do
Let me
they
check.
grow them as crystals? I don't know.
No, let me check. Let me check. Let me see what is the.
Yes. Are you using MirrorThink?
Yeah, no, but also I'm now trying to
Sure.
silicon product wafer production process. So also essentially they have a seed crystal.
Hmm.
They have like essentially if you
Yes.
like a kid when we were kids,
Yeah,
like we
yeah, yeah.
had this what you call hypersaturated
Yeah, 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 yeah.
like solutions, and we would make it. So apparently there is a like a crucible,
Mhm, mhm,
then they are melting melting what do you call like silicon,
mhm, mhm,
and then they have a single crystal so they make a um like a seed,
mhm, mhm.
and then they pull it out, and it becomes essentially it would become like
Oh,
around
okay.
something like around
Oh,
one
yeah, because they make it like a big cylinder, no? And
yeah,
then they
yeah,
cut it into wafers.
yes. And I've
Okay.
seen this when I visited ASML. I've
Mhm.
seen the like the whole
Oh, SML also makes the wafers?
no, 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 but they show it. They have a experience center
Mhm, mhm,
that they show all of this
mhm, mhm.
steps. So next time maybe we can have essentially some way that we can show the what do you call it, the screen
Yes,
of the
yes.
computer. But then that's where it comes, and then you need to make an oxidation layer on top,
Yeah.
and so it's so interesting for me that there are some basic, if you think of it as basics, the principles are basic,
Yeah, yeah, yeah.
apart from some of them that is kind of the PN junction by itself, like the
Sure.
diodes and um, the principal working, which is a quantum effect. But so they put water on top and they create this silicon oxide layer
Mhm,
on
mhm,
top,
mhm, mhm.
and then they put like chemical mask on it,
Yeah, yeah, yeah.
and then they have a photolithography
Yeah,
that is
yeah.
essentially where they do, I don't know, did you do at school making
No.
circuits
Yeah,
like
no,
with
I didn't. You did
photolithography?
that?
It
Really?
was like it's a very simple thing. Like we what we did, we used to draw like not the circuit boards,
Yeah, yeah, yeah.
right? Not
Like the
the chip
PCBs? Yeah,
PCBs,
yeah, yeah.
right? So it's just it's a piece of plastic.
Mhm,
On top of it, there is a layer of copper,
mhm,
and
mhm.
we would make what do you call it? A layer there that we would draw
Mhm,
or cut
mhm,
and stick it on top,
mhm, mhm.
and then we would like essentially wash it in acid,
Ah, okay.
So
So
the
it's a
this
similar.
yeah.
Okay. Okay, I see, I see. But it's not like photoresist. It's a different, like you etch it like by hand.
No, but with acid.
Okay, yeah, 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 I
Yeah,
understand.
etching it was in acid. But also you have two types of etching: wet etching and
Hmm.
um, dry etching, which
Yeah,
is
yeah.
essentially you're removing that layer of silicon oxide,
Mm-hmm, mm-hmm, mm-hmm.
and then you can essentially do based on that you can do doping,
Yeah, 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 yeah,
different types of doping.
yeah, yeah. You need to have the, yeah, like the photo, like for a long time actually, they actually made chips with just normal like photography chemicals, like photoresist chemicals, like actually like Kodak and such was a big supplier at the beginning, uh,
Yeah,
and then it got very specialized. But yeah, for a while they just used normal kind of photography developing stuff, uh, and they actually made the patterns by hand. Like actually for like 20 years, like between the 70s and the 80s, like they literally used like rulers and they made the pattern by hand. Like they actually would make the chip diagrams by hand. There was a whole generation that could do that. That ability has been lost, I think.
but what would they do? They would use that as like on the on the what do you call projector.
Yes, I think there might be like a multi-step process. Like they would make the
That's a
pattern
mask.
on paper, and then from that they would make a mask or something like that. Still making the mask, I think, is the main bottleneck for, when you want to make a new chip. Because I was looking into it for a while, because I was thinking like, why is it so hard, like why is it so expensive? If you design a chip, why is it so expensive to produce it, and why can't they just make a lot of different chips in parallel, instead of making always one design. And apparently the main bottleneck is making the mask, same as making the mold for like plastic products, you know, like
Hmm.
injection mold, like in making the mask for a semiconductor for a chip, takes weeks and weeks of very specialized work where they need to iterate on it, they need to correct it. It's not something that has been automated fully yet. Uh, I think it's one of the bottlenecks why it takes so long to make a new chip and why it's so expensive. Uh, but yeah, anyways.
So actually, I now that I think of it, maybe I need to invite one of my friends that is in semiconductor industry working inside to get a bit more like meat on the bone
Yes,
how
yes, I think that would be very cool.
yeah that we can do.
There's a lot of people we can invite if this goes well. Uh,
Yeah, but I'm looking at now, for example, like we are talking about one step which is a photolithography,
mhm,
but they are like I have now in this more than I think 50, 60 different instruments
mhm, mhm,
that they're using it for uh, in a fab or in
mhm,
a semiconductor R&D.
mhm, mhm,
And this is so cool
mhm,
because now, for example, this growth means that a lot of these companies now have a lot of growth opportunities,
mhm,
and now they can essentially uh, better capture a piece of this pie. You
mhm,
know what I
mhm,
mean?
mhm.
That's the challenge that we have right now. Is that like um,
Yeah,
if this supply chain, if you want to bring it to over, you need to be able to sell and buy all of these devices and find what are the best, for example, like mask aligners, what are the best what do you call it, automated optical inspection, what are the best inline metrology tools.
yeah, because
This
everything changes. Like the smaller you go, it's not just a different in scale. Like once you go to once the everything moved to EUV, everything became so much harder. Just making a light source, like a light bulb, that can produce EUV at that intensity, it's incredibly hard. And there was like an investment of like a couple billion to produce just the source. I think it's I was listening to the book, the
mm,
chip war. He explained it there. I think they use a droplet of lead and they like explode it and many times the temperature of the sun to produce this EUV light source. And then you need special optics that were mainly made by Zeiss, who we work with. Uh, Also, Zeiss got an investment of like 1 billion from ASML to build the optics that could deal with extreme ultraviolet. You know, also for like R&D and quality control failure analysis. When you're talking about 14 nanometer, 9 nanometer, 4 nanometer, 3 nanometer, you suddenly need like imaging instruments that can look at things at the atomic level, and suddenly stuff that was built for scientific applications is relevant now. Which is why all the companies we interact with are so excited to get in there.
Yeah, these companies, I call them the coolest companies that nobody knows.
Yes.
Literally, they are not in popular science or popular media.
At least they are not as hyped up as Google or Microsoft, but like actually they make, well, they don't make more money than Microsoft, but they make more money than a lot of oil companies, a lot of banks, and no one knows about them.
Yeah, and it's kind of like very. It was very hard. For example, a company like ASML a few years ago, nobody really knew.
Mm.
In If you would talk about ASML in Netherlands, nobody really knew them, and still they don't know them. But like now, there are a lot of. I'm looking at the list of companies that are working in this industry
Mm.
that you would not even know, like a company like KLA,
Yeah, KLA, yeah.
right? I mean,
I think these companies just interact with the insiders.
let
You
me
know,
look
you
at
you
KLA
contact KLA. I think,
revenue.
yeah, you contact KLA when you want to build a new fab, and they set everything up. That's their job. But I think they're only known by a couple companies in the world, the ones that can afford building fabs. You
So
know,
do you know what is KLA's market cap?
what is KLA's market cap? No, I don't know.
How much is it?
I don't know. I would say like 20 billion. I don't know.
84 billion,
84 billion. Okay, okay,
right?
okay. That's more than Ford. We checked earlier. Like Ford is like 50 billion.
And Ford market cap is $40 billion.
Yeah, $40 billion. Yeah.
So, and how many people know Ford and how many people know KLA?
I know, I know. Like it's
And let me see ASML's market cap.
Yeah, SML I checked earlier. It was 6.6 billion, which is
No,
surprisingly low.
338 billion.
What?
The market cap.
No, sorry. I looked at the yearly revenue. Like the yearly revenue is surprisingly low, 6.6 billion. I think the valuation is very high because they have such strategic importance. But they don't actually make that much money, and they are not such a big company because they are really restricted by their production capacity. They can only
Not a
make
scalable company.
No, they can only make like 30 to 50 of these EUV machines a year. And there's not that many new fabs
No,
being
but they
built.
had 27 billion in 2023.
Are you sure?
Yeah, yeah. I think you were looking at the quarter.
Maybe it was a quarter. Yeah, you
And
said 30
you know
billion
what is their
earlier.
gross margin? 51%.
Really?
Yeah.
That's interesting because
Like,
actually
let
they
me
don't
see
do.
KLA gross margin.
Yeah, it's because they have the monopoly. Yeah, you can have big profits if you have the monopoly. Yeah, maybe I'm wrong then.
KLA's is
I was surprised as
59,
well.
60%. Let me see KLA revenue
Yeah,
2023. 10 billion
10 billion.
KLA.
Yeah, like some of our clients, they make like
Let's
25,
look
30
at
billion.
another cool company that nobody knows is outside of scientific arena is Thermo Fisher. Thermo Fisher is 42 billion.
42 billion now? Like
Yes.
that, last time I looked at it, it was 25 billion. And I guess it was a couple years ago. Did they grow that much? Maybe I'm misremembering.
But let me see at their market cap.
Maybe it's not as high because they're not.
210 billion.
Okay, okay. Still very high. Still very high.
Oh my god, like this is the thing that let me. So KLA was one of the companies that nobody knew,
Yeah.
like Cyber Optics.
Cyber optics, I don't even know. Like, what company is that?
Cyber Optics. Let me see. They make um so at automated optical inspections,
Mm-hmm.
right? So they
For like quality control.
yes. So let me see if I can see how many employees they have. Between 50 and 200.
It's not that much.
But there is Nordson
Mm-hmm. Mm-hmm. Mm-hmm.
Corporation. So is part of Nordson Corporation,
Mm-hmm.
which
Mm-hmm.
is 5 to 10K employees. So on LinkedIn, if you look at it,
Mm-hmm.
they have 2,355 88 associated members,
Mm-hmm. Mm-hmm.
but they say that it's between 5 to. So let's see Nordson revenue. 2.6 billion
Mm-hmm.
revenue,
Mm-hmm.
right?
Mm-hmm.
And the other thing is, another thing that's so there are like I have more than 90 companies that I would like to know. For example, Hitachi makes stuff for
Hitachi is a big one. Well, they do a lot of other things as well, but yeah.
Tokyo Electronic Limited, Applied Materials.
Applied Materials is a big one. Actually, they are the main supplier of the layers on top of the silicon. What do you call that again? The coating.
The mask? No.
No, 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 no. The
The
different
polymer.
layers on top of the silicon. Like
What does
deposition and
Yeah,
yeah. I think Applied Materials is the main
difficult.
supplier of those chemicals and the technology to build these
Let's see. I'm
layers.
looking at their product and services
Hmm.
in semiconductors. Enable the AI arrow. Everyone is using this AI.
They are also.
They have these humongous machines.
Well, it's the biggest demand
Net
right
zero
now.
acceleration.
AI chips. You
Yeah.
know, crypto went a bit dark, and now AI is a big demand.
Let me see. Let's ask Mirror think what they do.
Yes. Yeah, I checked this morning. Actually, I think it was something like that.
Does applied material
I think they're one of the companies
produce
that
for
stand
the
the most to gain from building all these new fabs.
deposition systems, as
Yeah,
you
the
said?
position. Yeah.
They're used to deposit various materials onto wafers. Etch systems,
Hmm. Hmm.
rapid thermal processing, which is systems are used for annealing, which involves heating the semiconductor wafer to a high temperature to change the electronic properties
Hmm.
of the materials and active dopants.
What is?
So
Can we have a small parenthesis? Actually, what is annealing? Like you're the physicist, you always
annealing
hear like quantum annealing and
annealing means that means essentially heating up and cooling down
okay, but what
in
happens
a
in that process?
controlled manner.
Does the what happens when you heat it up and cool it down? Does it align the electrons in a certain way? Like my memory has this vague idea of it.
So it says heat metals or glass and allow it to cool slowly in order to remove internal stresses and make it easier to work with.
Okay, so it's kind of like shaking shaking something so that it becomes more ordered.
Yeah,
Like
there are like they having quantum annealing means that they bring something in outside of a quantum states, like
mm-hmm,
in a more classical
mm-hmm,
temperatures that the system shows classical behavior, and then you cool it down
mm-hmm.
in order to, for example, let's say in like D-Wave, for example, they are famous for their
Yeah,
quantum
yeah.
annealing computers. What they do, they have these superconductive rings that they are their qubits.
This is a confusing thing because like annealing to me like it refers to rings, and I think it's not related, huh? Uh, like annealing is like Latin for making into a ring.
Really?
Yeah, yeah, yeah.
By the way, he's Spanish. That's why
Yes,
he
that's why anillo in Spanish is ring. That's why.
etymology. Let's see
Yes.
etymology of annealing. Uh, anneal origin comes from Old English. From
Is it
Old
Old English?
English is to burn, bake, from
Oh,
burning.
so maybe it has a different. So maybe it's just a coincidence that it sounds like the ring.
So it's called unailan. How come that every time I'm the dyslexic person, the whole reason that I started this company was not to read anymore, and I end up reading all the time.
Yeah.
Yeah,
Okay, so it's
let's
totally
go.
unrelated to rings, but so essentially,
Maybe like there would see like etymology.
so annealing generally means to bring to a higher energy state and then let it kind of go down to the stable energy state. Is that correct?
Yes, so essentially to, I think it has different meanings or different ways to do it in material science
Mm-hmm.
context or in quantum context,
Mm-hmm.
but this is essentially what um,
Mm-hmm.
that is what it is. But let me go on the rabbit hole of annealing.
Sure.
In the Middle English, annelen, annelen from Old English. What is this AE attached to each other? How would you
It's a
pronounce?
vowel. I don't know. Yeah, it depends, but
To set fire, and then from Proto-Germanic, Eilan,
mm-hmm.
and from the same root meaning to burn,
Okay,
ash.
okay.
So it's not,
So
unfortunately, it's not
it comes from
Latin word.
Germanic. It's not Latin. Okay, that's quite interesting. So I was getting confused with the rings. But anyways, going back to the,
Why annealing is used.
I think like we started this tangent on the silicon wafer. So essentially, what you meant is that they heat it up and cool it down so that the structure is more regular,
Yeah.
so that it's more precise. Huh? What are you finding?
So it says that it's dopant activation. So they dope for, because silicone is not a semiconductor, or like it is semiconductor, but you need to essentially dope it with the P
Yeah,
or N types, like, or like the things that introduce extra electrons.
silicon. Silicon is an insulator, no?
Is an insulator,
Yeah.
but it's a smaller band gap.
Mm-hmm.
So it's called dopant activation. During the doping process, impurities, dopants are important introduced into the semiconductor materials to alter its electrical properties. Annealing is used to activate these dopants by providing the energy needed for them to move into a substantial
Ah,
substitutional
ah,
position within the crystal structure. So
I
they moves them,
understand. Okay,
which
yes.
allows them to effectively change the material's conductivity. This I need to do more research. Repairing crystalline damage.
Yeah,
That is what you were saying, and stress relief. So, for example, like if you heat it up,
yeah.
then the atoms would shift.
It's like having a box of balls, and you shake it, and they become more regular.
Yeah,
They
yeah.
get into a crystallized structure.
Improving electrical properties.
Like the doping reminded me, like the annealing of the doping.
How do they
You
do?
remember this whole thing with the superconductors, like earlier, like last year, mid last year or something like that, like the superconductor thingy, where
Yeah.
they thought they found a superconductor, and there was this whole conversation about doping the material and in what position in the crystalline structure it should be, and how that was like getting the copper in the right place, how that was really hard. And they were saying, okay, like the samples they were getting, they were impure, and they struggled to get the copper in the proper position. In the end, it didn't matter. It was a false alarm, but there was a whole conversation about that.
So I asked how is doping is done
Mm-hmm.
in ion implantation. Is the most common method of doping. It involves accelerating dopant ions to high energies and then directing them into the semiconductor substrate.
Mm-hmm.
That is why they need this, what do you call it? This layer,
Mm-hmm.
protective layer.
Mm-hmm. Mm-hmm.
And when they essentially like they do the photolithography
Yeah.
to remove those parts,
Mm-hmm.
and
Mm-hmm.
then they kind of they wash it with acid or like with the gas. So then they heat up this, they bombard it with these ions,
Mm-hmm.
and then it penetrates
Mm-hmm. Mm-hmm.
the silicon.
Right. So they embed it in there, and then
Yeah.
they heat
So
it
those
up so
areas.
that it gets in and cool it down so that they get into the right position.
Yes, the process is highly controllable, allowing to precise control over the dopant concentration and distribution.
Mm-hmm.
After ion implantation, an annealing step is used to require to repair the crystal damage and activate the dopant.
So when you bombard the silicon with the ions, it kind
Good
of
job.
breaks up the
Yes.
crystal. Okay.
Then the other one is diffusion, because when I was doing actually studying physics, we were doing solid state physics and
Mm-hmm.
theory. I was always asking like, how do they do these PN junctions? And like they would
Mm-hmm.
not stick them together in diodes and
Mm-hmm.
in transistors, but now I'm learning it after 20 years already. So
You're not
diffusion,
an experimentalist.
no,
That's
no.
the thing. Big on maths and theory. Yeah?
Yeah, I like those more
Well, you did
because
some
it's not like
simulations as well, but
it's not really like I'm clumsy with real world,
actually, my cousin, she's now studying. She's now finishing the degree in physics and maths, and she says, yeah, she's terrible in the lab. She has a bunch of accidents. Maybe I shouldn't talk about this in public, but anyways, you don't know
She
who
will
she
not
is.
listen.
No, she will. No one will listen, at least to this first one. But yeah, she was saying this that she was very clumsy, so she wanted to go into maths and applied maths
Yeah.
and epidemiology and such. Yeah.
So after this tangent,
Yes. Sorry.
diffusion, the semiconductor is exposed to a dopant source at the high temperature. The dopant diffuse into the semiconductor material from high region of high concentration to low concentration.
Mm-hmm.
The depth and the concentration of the dopant can be controlled by the temperature and the time of diffusion. So the other one is essentially bombarding, essentially ion gone.
Yeah. Yeah. Yeah.
This is like essentially similar to, let's say, TVs, old CRT TVs.
Right. 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 Yeah, yeah.
I'm assuming here, huh? I will read and
I'm sure it's way more complex nowadays, but I think the first ones they were probably just a normal. Is it like a magnetic? They just accelerate ions with a magnetic field,
no, I think the electric field. I need
electric
to,
field. Okay.
or maybe they do it also cyclotron. No, I don't think so.
Hmm.
I need to check. Let
But you
me
are
ask
saying
it.
so after the annealing, the ions need to diffuse through the crystal.
No, no, no. They diffuse and then they anneal it.
Okay. Okay, that makes more sense. Yeah. 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 Okay, so they bombard it, then they help it spread through the silicon, and then they anneal it so that it gets ordered.
I'm asking how do they. So the other expectational
Mm-hmm.
growth. During this growth, a thin layer of semiconductor material is deposited on a substrate. The dopant can be incorporated in the gas phase during the deposition process, resulting to a doped layer.
Mm-hmm.
This method allows the growth of doped layers with different properties than the underlying substrate. So
Mm-hmm.
essentially, they have this substrate, they have it atomic deposition.
Mm-hmm.
This comes and grows,
Mm-hmm.
and then it's similar to vapor deposition or something. So alloying,
Mm-hmm.
making an alloy.
Mm-hmm.
This is a less common method where dopant atoms are mixed with the semiconductor materials in molten state.
Okay. Well, okay. Yes. Yeah. Makes sense.
Upon solidification, the dopant are incorporated into a crystal lattice. This method is typically used for compound semiconductor rather than silicon.
Mm-hmm. Mm-hmm.
In situ doping, so with time, in situ means time.
Mm-hmm. No, in situ means in place.
No.
Yeah. Yeah. Yeah.
So in situ doping occurs during the deposition of a semiconductor layer, such as during chemical vapor deposition, a molecular beam, dopant gas are introduced into a reaction chamber and along with the precursor gases. This becomes too complex
Yeah.
to.
No, I'm not following. That is fine.
Yeah. So I asked what is the way, why they, how they do the acceleration. With the most common one is ion implantation, so which is bombarding.
Yeah. Yeah. Yeah.
So with the ion source, the process. So I said, how do they accelerate
Mm-hmm.
these
Mm-hmm.
ions? So ion source, the process begins with an ion source where a gas containing the desired dopant element is ionized. The ionization is usually achieved by applying the electric field,
Mm-hmm.
which strips electrons from the dopant atoms, creating a positive charge ions.
Mm-hmm. Mm-hmm.
Once the ions are generated, they are extracted from the ion source using the electric field.
Mm-hmm.
The extracted ion are then directed into an acceleration stage of implanter.
Mm-hmm.
Acceleration phase, the ions are accelerated in high energies by electric field. This is typically done using a series of electrodes increasingly positive voltage. So
Mm-hmm.
essentially they have electrodes and meshes that they are essentially accelerating.
Ah. Okay.
They have it this called ion jets, that also the
Mm-hmm.
fanless jets.
Mm-hmm. Mm-hmm. Oh, like those Dyson fans that don't have the.
No, no, those are not. Like there are
Okay.
some that they do, like in on YouTube, if you search,
Yeah. Yeah. Yeah.
they have this the same thing that they make
Oh yeah.
propulsion
Yeah. Yeah. I saw
by
like some
accelerating.
prototypes of like planes
Yeah.
that were yeah with propulsion with ions. Yeah. 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 Ion engine. There's a lot of talk as well of making spaceships out of that. Yeah.
Then mass analysis,
Yeah.
because the ion source may produce a mix of different ions,
Mm-hmm.
it is necessary to select the only desired dopant ions.
Oh, okay.
This is achieved by using mass analyzer, which separates the ions based on, oh, this is
This is
cool,
like mass
charge
spectrometry,
ratio.
no?
This most common by a type of mass analyzer is magnetic separator. This
Yeah,
is
yeah, yeah.
cool.
So this is how mass spectrometers work as well,
Yeah.
no? Where you separate, yeah, yeah.
And then ion shaping, which is essentially lens and the
Mm-hmm.
scan.
Mm-hmm.
The selected ion beam is then shaped and focused using magnetic and electron lenses. These are also very cool things.
Oh, so it has a very precise beam then.
Yeah,
It's not
because
just
no,
bombardment.
because you need.
So because you need even in every at every point, or why does it need to be so precise?
So I need to ask.
Mm-hmm.
So here it says the beam is scanned across the target silicon wafer
Yeah, that makes
in a
sense.
controlled pattern to ensure uniform doping across entire
Yeah,
surface.
yeah,
So they can
that's what I
essentially
found.
scan it.
Yeah, yeah, yeah. It was a similar thing as well with lithography as well. They do it in small portions and they scan through it. Like a big breakthrough, I think in the 80s, there was this company in the US that made this. It was a small company at the beginning. I don't remember the name. It was in the book, uh, where they started making these steppers like for lithography, where it would go very
You mean the
evenly.
light source
Yeah,
for
yeah, yeah, the
lithography?
light source. So it's a similar process, except like instead of the ion beam, is a light source for the lithography. But they took over the market for like a decade. Then they went down. But these stepper lithographers were a big deal for a while. Yeah. Anyways.
So then is implantation and then cooling.
Mm-hmm, mm-hmm,
So it says now the accelerated ions collide with the silicon wafer,
mm-hmm,
penetrating the surface and coming to a rest at a depth determined by their energy.
mm-hmm, mm-hmm.
So I will go and again try to describe it in more plain words.
Sure.
Then cooling to prevent wafer from overheating during the implantation process is typically held at a controlled temperature, often using cooled chunk, uh, cooled chalk,
Mm-hmm.
or by passing coolant through the wafer holder.
Yeah, actually, I can imagine if you're bombarding the silicon with ions, a small part of it becomes really hot and it messes the whole purity of it.
Yeah.
Huh?
So essentially, so what they do, they create um, with ion discharge.
Mm-hmm.
They create these ion sources, like
Mm-hmm.
they make ions. Then they accelerate it to essentially with having positive and negative, what do you call it? Uh, Arrays of what do you call
Yeah, the grids.
grids,
Yeah, I understand. The
and then
meshes.
they need to make sure that is a ion with the same, because it might be one -1 or +1,
Ah, okay.
like, or 2 or something.
Right.
You know what I mean?
Yeah, yeah, yeah,
So the charge, how
yeah,
many
yeah, yeah,
electrons is missing,
yeah, yeah,
they want to separate that.
yeah.
So they accelerate them around a radius with a magnetic field, and they curve differently based on their charge.
Right. Yeah, I remember studying this in high school.
Yeah.
Yeah, based on the on the electric charge in the magnetic
Yeah,
field,
it's
they
essentially
rotate in a
if
different
you want
rate.
to go, like, it's like at the when you go fast around the curve,
Yeah, yeah, yeah,
the faster the tighter the circle is,
yeah, yeah,
in like when you go karting,
yeah, yeah.
you need more friction or
Mm-hmm,
more downward, like, central force.
mm-hmm,
So,
mm-hmm.
and then so it means that, like,
Yeah, it makes sense. The ones that are attracted the most, they curve tighter, so they
yeah,
get separated. Okay. Yeah,
yeah,
yeah.
they are the bent most. And then here that's how they select. And I think here then becomes quantized, like, because the number of electrons are quantized.
Mm-hmm.
So you would see like, what do you call it, radiuses, specific radiuses that these ions.
Right. Like specific lanes where the
Yeah.
ions fit in. Okay, okay.
And then
Mm-hmm. Yeah, then you bombard the silicon. You introduce the ions into the silicon, which heats it up, so it needs to be cooled. You need to
yeah,
let the ions diffuse through the silicon,
yeah,
uh, so that they are evenly spread, and then you need to anneal it so that they get into the right positions.
yeah, yeah, yeah,
So, anyways, we started talking about this because we were talking about the ASML and applied materials and such, and it's important to realize that ASML, they have a big monopoly on the lithography, but there's a long process before the lithography to prepare the wafer and do all the layers and the deposition and the doping, which is done by other companies like Applied Materials. I think there are some others. And then we also earlier we discussed how to make the wafer itself, which there are other
yeah.
companies specialized in that.
And then afterwards, essentially, there are long list of companies that do a lot of test and quality control tools,
Yeah.
and like failure analysis tools and such.
Yeah, that's another one. Then looking at the actual chip and seeing,
Yeah,
what defects it has and how to improve the yield.
yeah.
Yeah.
But then all of this, the cool thing is that I was reading also McKinsey and different reports. They say by 2030, the semiconductor industry will pass $1 trillion value annual sales. The whole.
We need to be careful though, because we are working with these, precision analytical instrumentation companies, and this does not necessarily translate to big growth for them. I mean, certainly there's a lot of growth, but I was looking into it this morning. I was looking into how much the current investment in semiconductors, trickles down to this precision
Suppliers.
instrumentation. Yeah. So a lot of it is just building the fabs and just construction and the kind of manufacturing equipment. And I looked into it, and if a fab costs like between 10 and 20 billion dollars, they do spend quite a lot on precision instrumentation, but it's only like a couple 100 million out of that they invest on, AFMs or electron microscopes to analyze the failures in the produced chips, and to try to iteratively improve the yield. But these are offline instruments, so it's a small part of building a new fab. It's still, a couple 100 million. And if you add up all the fabs being built this year, which is a lot more than usual, I think, there's two being built in Japan. Yeah, there's, I don't know, a few building in the US, I think three or so, a bit less in Europe. If you add it all up, it's between 1 or 2 billion for the year, just for instrumentation in failure analysis. Then there's also R&D. So the instruments we work with, they are used a lot in R&D, to look at the surface of the prototype chips you are making, to experiment on how to make smaller and smaller transistors. R&D investment is also big, uh, but for example, there's only a few companies in the world that are investing in this type of instrumentation and doing this type of R&D. For example, Intel, they invest about 20% of their revenue in R&D a year. They make, I think I saw about 20 billion a year. And no, 12 billion a year. No, sorry. Um, the revenue is 60 billion a year, and they invest about 12 billion a year in R&D. And out of that, more or less a single percentage point, like a single digit percentage, is invested in precision instrumentation. So if Intel invests 12 billion in R&D, they might invest again like, between 100 and 500 million in precision instrumentation. And if you add this between Intel, TSMC, Samsung, which are the main investors in R&D in this area, like TSMC only invest about 8% a year in R&D. Samsung is a bit harder to see because they have so many other businesses and they don't really report semiconductor R&D separately. But in total, again, it's about between 1 and 2 billion a year in precision instrumentation. So if you add up the fabs and the R&D, we have a market of about 3 or 4 billion, which is significant, but it's not the 300 billion you were talking about.
Yeah, there is. Yeah, the thing is that these companies are having a lot of diversified market, right? They are one is semiconductor,
That's
one
true.
is
Yes, they are making also so much money out of batteries,
pharmaceuticals, batteries,
solar.
right?
Yeah,
Solar cells, energy, petroleum, polymers,
yeah.
and yeah, that's it. But let's wrap it up.
Yes.
This is for the first time is very good. My water is over empty, so you see I'm crying. It's not because I'm emotional or something. It's
Yeah,
just the air.
allergies. Yeah.
Air. So this was enjoyable.
Hmm.
Thank you very much. Um, we will try to do this more often and see how deep we can go and what subjects we can cover.
Yeah.
Yeah. Thank you very much.
Yes.
Have a
Cool.
great day.
All right.
Bye.
Bye bye.